In this video, I'm going to talk about categorical predictors in multiple linear regression. So for our example, we have a service company, and they've recorded information on their last 10 service calls, and they recorded months since the last service, which is X1, and then they've also recorded whether the type of repair required was electrical or mechanical. And we're going to try to incorporate this type of information into the model. And then the response is quantitative, and it's the repair time in hours. So this variable here is a qualitative variable as opposed to X1, which measures the month since last service, which is quantitative. These numbers are meaningful measurements that indicate that the variable is quantitative. These are words. And so the least squares method, which is used to estimate the multiple linear regression model, isn't going to be able to handle this because it needs to work with numbers, not with words. So one way to handle this is to code this information into numbers. And the way we do that is using a dummy or indicator variable consisting of zeros and ones. And in particular, we're going to use X2 as an indicator variable that will have the value 1 if the type of repair is electrical, and the value 0 if the type of repair is mechanical. And it turns out that if we use a multiple linear regression model with X1 and X2, that we end up with results that we can meaningfully interpret in terms of the type of repair. So let's see how to do that. So let's estimate the model first, and then we'll talk about how to interpret the results. So it's a linear regression model, as usual. And the response variable is repair time, and two quantitative predictor variables, X1 and X2, because I've turned this qualitative predictor into a quantitative predictor by using the indicator variable. And then let's just OK that and get the results. Okay, make it a little bigger so we can see, and scroll down and find the numbers that are going to tell us the equation, the estimated equation. So that's these numbers here, 0.930, 0.388, and 1.263. So I already copied these numbers over into here. Okay, let's get a little more accurate here. Let's go one more decimal place. There we go. Okay, so we have our equation, and we can use our equation to predict y for particular values of X1 and X2. So let's go through a couple of those calculations to see what's happening. So for this first observation with X1 equal 2, X2 equal 1, we have 0.9305 plus 0.3876 times 2 plus 1.2627 times 1. Okay, let's have a look at this one. 0.9305 plus 0.3876 times 6 plus 1.2627 times 0. Okay, let's look at a couple more. This might seem like a little tedious and like, why is he doing this? But I want you to see the pattern of what's going on. This one's 0.9305 plus 0.3876 times 8 plus 1.2627 times 1. Let's do one more. 0.9305 plus 0.3876 times 3 plus 1.2627 times 0. Okay, so what's happening is this last piece of the equation, B17, the 1.2627, is multiplying either 1 if it's an electrical repair, or 0 if it's a mechanical repair. So let's look at the mechanical repair first, because that's a little simpler. This last piece is just 1.2627 times 0, then this last piece, it goes away. Okay, I could actually just erase it, and I get the same number here, 3.2562. Okay, it's 3.2562 if that piece has gone away, or if it's there, it's the same number. Okay, so it looks like, let me just get rid of it again. There we go. It looks like the equation that's used to predict y when we have a mechanical repair is more simply stated as 0.9305 plus 0.3876 times x1. So that's what I've represented over here on the right-hand side. For mechanical repairs, x2 is 0. And if we think of this in terms of an intercept and a slope of a line, the intercept is 0.9305 and the slope is 0.3876. The slope is what's multiplying x1. Okay, so this is an equation that we derived from the estimated regression equation for the whole model, but it only applies to the mechanical repairs. Let's try and do the same thing for electrical repairs. Okay, so what do we got? We've got 0.9305 plus 0.3876 times x1 plus 1.2627 times 1. Okay, so I could replace, instead of saying B2 there, I could just type 1. Because for electrical repairs, x2 is 1. Okay, and see 2.9684, it's the same number whether I have B2 in there or 1. It's always 2.9684. So it looks like this is the equation that works for electrical repairs. Okay, but let me just rearrange this equation a bit. I don't even need the times 1, really, because a number times 1 is the number. Okay, the times 1 doesn't change it. I could rearrange this just a little bit, though. Let me move that B17 up to here. Okay, and then I'm just gonna put some parentheses around that piece. Okay, well, I'll just hit return, make sure it's still the same number. Yeah, still 2.9684. I haven't changed the calculation. I've just rearranged the order in which we do things. So now we could think of the equation for predicting y for electrical repairs as being 0.9305 plus 1.2627, that's this piece, plus 0.3876 times x1. Okay, so if I think of this in terms of intercept and slope, again, it looks like these two pieces together, added together, are the intercept, and then this is the slope. Okay, so that's what I've written over here for electrical. Okay, the intercept, 2.1932, is the sum of 0.9305 and 1.2627. If I add those two numbers together, I get 2.1932, and then the slope is just 0.3876. Okay, so I added these two numbers together to get the intercept for electrical repairs. Might be easier to think about this in terms of this graph. So in this graph, I've got repair time on the vertical axis and months since last service, x1, on the horizontal axis. And the data points are colored according to red means electrical, blue means mechanical. And then the two regression lines here are these two lines here. So look at the mechanical one first, that's the blue line. That's got an intercept of 0.9305. If I trace this line back to where it crosses the axis, it would cross at 0.9305. And the slope, the rise over run for the blue line, is 0.3876. The red line, on the other hand, is this line here. If I back that up to where the intercept would come, it would be about there. That's 2.1932. And it has the same rise over run, the same slope of 0.3876. So that's a good way to think about this particular model when we have one quantitative predictor and one qualitative predictor, and we've used an indicator variable to fit the model. It gives us results that are equivalent to two parallel lines. How do you get this graph? Okay, let me show you how to get that graph. I'm going to use Excel stat again, but this time, instead of using the indicator variable, we'll just select X1 for the quantitative predictor, and then I'm going to check this box where it says qualitative under explanatory variables, predictor variables. I'm going to check that, and watch what happens up here when I do that. It'll change from saying linear regression to saying ANCOVA. ANCOVA means analysis of covariance, and it's the name given to this particular model where we've got a quantitative predictor and a qualitative, I didn't select it, a qualitative predictor. Okay, so you might think, well, didn't you say a few minutes ago that the least squares method can't handle words? Well, the computer does something clever here. It recognizes that this is a qualitative predictor, and it creates an indicator variable that's used internally by the software algorithm to estimate the model. So it doesn't require us to create the indicator variable. It kind of does it internally without us having to worry about it. So let's take a look at the results. Taking a bit of time to draw a whole bunch of graphs. Okay, it's done now. And if I scroll down, okay, we get the same results as we got before. Here are the three numbers that are used in the estimated regression equation. This 0 here is because it adds a row to this coefficients table that's representing mechanical repairs where the indicator variable is 0. So that's why there's zeros here. But what's going to be new is this graph. So it didn't draw this graph before, but now it does because it recognizes that this particular model can be represented like this as a graph with two parallel lines. Okay, I'm going to do one last thing that goes a little beyond what we've just talked about, and that is to think about what would happen if I added an interaction between the quantitative predictor and the qualitative predictor represented using the dummy indicator variable. Okay, so essentially I'm going to have an x1 times x2 here. What would that look like? Well, we can easily see what that would look like if we fit the model and add an interaction. Okay, so there's my model, and then under options, I'll add an interaction. And when it asks me, I'll select all three terms. And now it's going to fit that interaction term. And for the picture with the two lines, the interaction term allows the two lines to have different slopes as well as different intercepts. So we'll see that down here. There we go. Okay, so the blue line and the red line have different slopes as well as different intercepts. And then the question you could ask yourself now is, well, these are the slopes of the lines in the sample. Are these two slopes different enough that in the population I would expect the slopes to be different as well? Or are they close enough to being parallel that I can't really rule out the population lines being exactly parallel? And that's actually the case here. These two lines are close enough to being parallel that we can't rule out in the population the lines being exactly parallel. And we know that because if we look at the interaction p-value, which is right here, it's not significant. It's bigger than our usual 0.05 significance level threshold. So we would not be able to reject the null hypothesis that says the interaction effect is 0. And so what we would conclude from that is that this model is inferior to the original model that we fit, where we had parallel slopes. Okay, so that's categorical predictors in multiple linear regression.